Hello everyone, I'm Tuan, and together with my teammate Phan Mạnh Ha, we are presenting about our assignment 3 for the course Data Communication and Eccentric Computing. Okay, here's my student card. You can see here. Okay, now we will move to the overview of this assignment. In this assignment, we implemented a fully functional network design with four subnets, VLAN segmentation, inter-subnet communication, and server access. All of these are simulated in the Cisco packet tracer. Now, let's walk you through the main task as you can see in the slide here. Now we will move to the task one. This task is about the network design and configuration. We created four subnets, three subnets for the four hosts using /29 and one for a host using the /28. This satisfies the classic private addressing requirement and ensures the IP space is used efficiently. As you can see in the slide here, here's our network design. Um, and here is our packet tracer topology. Router are interconnected using the point-to-point link with like 30 subnets. OSPF has been configured on routers to enable dynamic routing and maintain reachability across the network. Each subnet is assigned to a separate switch and connected to a corresponding router interface. Now, let's move to the demonstration for the task one. Okay, let's start by verifying the IP configuration. I will take the PCB2 here in the subnet 2 for the example. You can see with the PCB2, we will have the IP 192.168.1.11 with the subnet mask /29, as you can see in the topology design here. And as I presented before, we implement the OSPF for on the router to ensure the connectivity for the whole network. Okay, I will take the router B for the example. Firstly, I will show the IP route for this router. You can see this IP is matched with the topology design here. And now I show you the OSPF neighbor. As on the router, we'll head to the OSPF neighbors. For example, in the router B, we will have the neighbor ID here, including the 1.1. This is the connection with the subnet A, and 1.17. This is the connection with the subnet C. So now I show you the demo for the sending message across on the subnets. For example, I will send message from the PCB4 in the subnet 2 to the subnet 3 here, and it is sent successfully. And I send from the subnet 3 to subnet 4, and it's also successful. And for example, I send from the subnet 2 to the subnet 4, as you can see here, is successful. And also send from here to here, from the subnet 1 to the subnet 2 is also successful. By sending messages successfully, we can verify that the layer 3 connectivity across all the routers here and ensures OSPF is functioning correctly. Now, let's move to the task two. This task will focus on the layer 2 implementation. We will implement the VLAN for a subnet. In subnet A, we split the network further using VLAN 10 and VLAN 20. Each VLAN has two PCs assigned. This setup will help us to test the intra-VLAN and inter-VLAN communication. VLANs are mapped to the sub-interfaces on the router A using 1Q encapsulation. As you can see here in the slide, here's the design of the VLAN for the subnet A. And as you can see in the topology design here, we have VLAN 10 and VLAN 2 config for the fast Ethernet 01, 02, 03, and 04, as you can see here. Now, let's move to the demonstration for the task 2. Let's begin by checking the VLAN configuration in the subnet 1. Okay, you can see here, we will have two available VLAN here, including 10 and 20. 10 is assigned for the fast Ethernet 01 and fast Ethernet 02. In the other hand, the VLAN 20 is assigned to the fast Ethernet 03 and 04. Okay, now we will test the intra-VLAN communication. I open from the PCA1 to PCA2. Okay, it's successful, and because it's same the VLAN 10, and going from the PCA3 to PCA4 is also successful in the VLAN 20. Now let's bring from the VLAN 10 to the VLAN 20 here. I bring from the PCA1 to PCA3. Okay, as you can see here, it's failed. Because these devices are in different VLANs and no layer 3 routing is configured between them directly. This thing should fail. Okay, so as you can see here, we also configure the drone for the VLAN 10 and VLAN 20 from the switch to the router. Now let's test the layer 3 connectivity. As you can see here, we define a sub interface for the VLAN 10 with the Ethernet 10.10 Now I open from the VLAN 10 from the PCA 1 to a PC in subnet 2. As you can see, it's successful because we configure the inter-VLAN routing using sub-interface, and OSPF is distributing the route. This ping should succeed. Now, let's simulate a failure here by shut down the interface Internet 1.0. Yeah. After that, I repeat the ping from the PCA 1 to PCB4, and as you can see here, it's failed. You see that, but when I ping from the PCA 1 to PCA 2, it's still successful. You see that the intra-VLAN traffic still works because it's handled entirely by the switch at the layer 2, but the inter-subnet ping will fail because layer 3 routing is now unavailable. So to conclude, intra-VLAN communication succeeds even when the router interface is down because it's handled entirely at layer 2 by the switch. So through this demo, we will satisfy all the requirements, including two VLANs in one subnet, real-time ping testing, layer 2 and layer 3 behavior comparison, interface toggling analysis.
Hello teacher, I am Tuan and my student ID is 4026698. For task 3, I will evaluate layer 3 performance by clearing the IRB table on devices in subnet B and begin a host in subnet C. I will analyze how layer 2 and layer 3 change in ingress and its egress point across the network and provide detailed explanation of address changes and router interface between subnets. Let's divine. So the first step, I will clear the IRP table of this PC by click to the PC, go to desktop, go to command prompt with the command IRP dash minus D to clear the IRP table and IRP dash minus A to check it, and it will show you no IRP in child files. And now I will initiate a ping from PCB1 to BCC1 to recache the IRB table, focusing on the IRB resolution and send an ICBM from subnet 2 to subnet 3. And in simulation mode, I've been from this PC to this PC, and you will see two BDU here. One is ICMP, is ensure the request that queue until the IRB reply is received, and the IRB here, the IRB request is here is a broadcast to find Tuan router P mark, and it's not encapsulated in the layer 3, and in the layer 2 it has destination mark is of the PCP1, and the destination mark is unknown. The IRP payload includes source IP and target IP. Source IP is a PC and target IP is a router. And now capture 2. And as this Tuan router B will flood this broadcast to on port, including Tuan router B. And at Tuan router B, the router B responds with the MAC address here. You will see here the subnet now is of the router, and the sub IP is of the router, and the target MAC now is the PC, and target IP is of the PC, and the router will respond this to the BCB1 through the Tuan switch B. After this, you will check the IRB table of this BC here, and now the BC will send the ICMP to the BCC1. From the BCB1, send ICMP to the switch B through the layer 2. It's just beyond the MAC table. You will see here. And the switch B sent to the router B. At Tuan router B, the IP header will attach here. And at the layer 2, the layer 3 remain unchanged, and layer 3 remain unchanged here to send this ICMP from Tuan router B to Tuan router C. But the router will decapsulate the Ethernet frame, removing the layer 2 header and check its routing table. It routes the packet from the Tuan router B to the Tuan router C through the FA01 and FA00. You will see the remain IP and the layer 2 frame will change. So at here it's still the ingress packet retain the IP of the destination and the target IP, but the layer 2 will swap. The switch forward to PCC1 based on its MAC table, completing the loop, and as here the ICMP echo reply follow the reverse path from PCC1 to PCP1. At each hop, MAC address will swap, and while the layer 3 remain with source destination and IP. And for task 4, I will configure a web server in subnet 4 which is designed for a host. I will ensure network-wide access, test connectivity, and explain the OIS encapsulation process. And this is my implement design for my system is a web server here for it. Now let's try an HTTP request from BCA1 with the Tuan web server with the simulation mode and click it to PC, choose web browser, fill URL with your host IP. Go. So the HTTP used in the OIS model you will see here. At layer 7, the server grab an HTTP response with web-based data based on the client request, including header like content type or content length and something more like this. Okay. And at the layer 4, a TCP header is added at here with the support 80 and destination port is 1034 here. You will check it here using the sequence number and just sum to ensure reliable delivery with acknowledgement number here. Use the way is three-way handshake. Like it's like that, it's just like that. And at the layer 3, it add the IP header with the sub IP is the IP of the server and the destination IP is the IP of the PC and the layer at the layer 2 it change at each hop. It's, you will see the process here from the PC to the tunnel switch A, it change the MAC address and the switch A to the router A, it change the MAC address and it changing at each hop. And let's check at the PC's model here. HTTP client it will decapsulate, layer high will remove, layer 1 transmit that the data bit, and layer 4 use port 1034 to deliver the browser, and layer 7 display the web page here. So I will test with this PC in the subnet 2. Click it, go to web browser. Okay. So it's successful. Let's go to another PC in another subnet tree. I will choose this PC. Go to desktop, go to web browser. And let's check. Yeah, it's successful. To conclude, we have successfully completed this assignment tree. This project deepened our understanding of networking principle, protocol, and layer communication. Thank you.